In mathematics, we love to classify things. Topologists do this by studying invariants, the homology groups, the fundamental group, the higher homotopy groups. These distinguish between spaces by counting the number of holes that they have. One of the earliest to ponder these invariants was Henri Poincaré. In the year 1900, he conjectured that every three-manifold with the same homology groups as the sphere is homeomorphic to the three-sphere. But then 4 years later, he discovered that this was not the case. There exists a three-manifold P called the Poincaré Homology three-sphere that has the homology groups of the three-sphere, but is not homotopy equivalent to it, so certainly also not homeomorphic. There are many ways to define P. Kirby and Charlemagne present 8 different descriptions, among them the unit quaternion's quotient by the binary icosahedral group, a link of the singularity of a certain complex hypersurface, and plumbing on the E8 graph, where E8 is the exceptional Lie algebra. But there is a particular geometric model for P due to Seifert and Threlfall. We can obtain P from the dodecahedron by identifying opposing faces. The dodecahedron has 6 pairs of opposing faces, but these are not quite aligned. We need to apply a 2 pi on 10 twist to a face in order to glue it to its opposing face. If we imagine flying through the interior of P in a spaceship, whenever we enter one of the faces, we immediately pop out of the opposing face, but with the little 2 pi on 10 twist. So we would need to travel 10 times through the interior of the dodecahedron before returning back to the starting point. But there's an interesting question that arises. What would happen if we were to fly our spaceship toward an edge? Consider this red point. One important thing to note is that the red point also appears in 2 other places. These are all the same point in P. Likewise, these blue points are all the same, and similarly these green points are all the same. So if we fly toward one of these red points, we would expect to exit from the other 2. Here's what that would look like. Let's take another look from a different perspective. Our spaceship flies toward the edge between the red and orange faces. We see that the green face is connected to the red face along its bottom edge, and we see that the green face is connected to the orange face along its top edge. So in fact we see that the green face extends behind the red and orange faces. And as our spaceship exits the edge, it emerges, traveling parallel to the green face. Now our spaceship flies toward the blue vertex. Locally we can see that the green face meets the blue face at the blue vertex. But in fact all of the faces meet this vertex. The orange one, the yellow one, the purple one, and the red one. And the interior of the dodecahedron is glued onto the blue vertex from every direction. We observe something surprising. Even around a vertex, P continues to look like R3. It's locally Euclidean. Although the 2 skeleton does have some branching, all of these faces coming together, after we glue in the interior of the dodecahedron, all of this branching vanishes. And therefore we see that P is a 3-manifold. We want to find the homology of P. To do this, we can leverage the fact that P has a cell structure. What are the cells of P? Well, in terms of 3 cells, we have the interior of the dodecahedron, which we will call V. The 2 cells are all of the pairs of opposing faces. It will be useful for us to have a 2D picture of the 2 skeleton. On this diagram, we can see the 6 2 cells of P. Each is an opposing pair of faces on the dodecahedron. We will label them C1 through to C6. There are 10 1 cells. Each appears 3 times on the diagram. We label them A through E and T through X. Finally, there are 5 0 cells. Each appears 4 times on the diagram. We label them 1 through 5. With these cells, we can now write down the cellular chain complex of P. Each cell gives rise to a copy of Z. To compute the homology of this chain complex, we need a better understanding of the boundary maps. Let's consider the leftmost boundary map. What is the boundary of V? Well, here's V, and its boundary consists of all of the faces. Each 2-cell is glued onto V twice, on one side and then again on the opposing face. But the gluing happens with opposing orientations. C1 is glued with a positive orientation, but also glued with the negative orientation. The same happens with C2, and again with all of the faces. As a result, the 2 cells cancel perfectly in pairs, and the boundary of V vanishes. So, returning to the chain complex, we find that the third homology group of P is Z quotient 0, which is just Z. A fact about compact manifolds is that the top dimensional homology group encodes information about the manifold's orientability. The nth homology group of a compact connected n-manifold without boundary is either Z when the manifold is orientable, or 0 when it is not orientable. In our case, H3 is Z, which tells us that P must be orientable. We also know that P is a path-connected space. Therefore, the 0th homology group is also Z. The fact that the top dimensional homology group of P is isomorphic to the 0th homology group is not a coincidence. It hints at a far deeper pattern called Poincaré duality. Let M be a compact orientable n-manifold. The kth cohomology group is isomorphic to the n-kth homology group of M for every k. Both the cohomology and homology count the number of holes that a space has. So, in essence, Poincaré duality points out that there is a correspondence between the k-dimensional holes of an orientable manifold and its n-k dimensional holes. In fact, this duality is one of the key ideas of Poincaré's 1895 landmark paper, Analysis Cetus. Poincaré's conjectures and his homology sphere both make their appearance in later amendments of this original paper. For us, Poincaré duality reveals the following. Recall that we would like to show that these two groups in the middle are 0, as this would mean that P has the same homology groups as the 3-sphere. We observe that the top and bottom lines are both Z. The cohomology and homology match perfectly in degrees 0 and 3. So, is it the case that the homology and cohomology groups are always the same? Well, in fact, this is not always true, but it will turn out that for P it happens to be correct. When we wish to compare two different groups, it's often fruitful to search for a short exact sequence containing both. Then the sequence will tell us information about the extent to which these groups are related. For us, this sequence will be provided by the universal coefficients theorem. We will only really need the case where k is equal to 1. Since P is path-connected, H0 is Z, and subbing that in, it turns out that the xth group is 0. This is because Z is free, it has a trivial projective resolution, and so the x group vanishes. But this greatly simplifies our sequence. We now just have an isomorphism. Suppose we somehow found a way to show that H1 is 0. What would this tell us about H2? Well, let's plug in H1 equals 0 into our sequence. What are the group homomorphisms from the trivial group into Z? Well, there's only the 0 map, so Hom is the trivial group, and therefore the first cohomology group is also 0. But by Poincaré duality, this is the second homology group. So then the homology groups of P would be Z0, 0Z, the homology groups of the sphere, and therefore we would conclude that P is a homology 3-sphere. It remains to show that H1 is equal to 0. We can use Hurewicz theorem. If P is path-connected, then the first homology group is just the abelianization of the fundamental group. So now we have a plan. All we need to do is figure out the fundamental group. Then if we 1. Show that its abelianization is trivial, then H1 is 0 and P is a homology 3-sphere. But we get even more. If we 2. Show that the fundamental group itself is non-trivial, then P and the sphere will have different fundamental groups. But the fundamental group is a homotopy invariant, so then we'd know that P was not homotopy equivalent to the 3-sphere. To compute the fundamental group, we turn to the Seifert-van Kampen theorem. Let P0, P1, P2, P3 denote the scaleta of P. Then Van Kampen's theorem says, firstly, that the fundamental group of P is just the fundamental group of its 2 skeleton, and that this is a certain quotient. At the top, we have a free product between the fundamental group of the 1 skeleton with the fundamental groups of all of the 2 cells, C1 up to C6. But these 2 cells are all homeomorphic to disks. They have trivial fundamental group, and so they vanish in the free product. At the bottom, we have the normal subgroup generated by the attaching maps of C1 through to C6. Let's start with the top. The 0 skeleton consists of the 5 vertices. We construct the 1 skeleton by adding in all the edges. What we get is this pentagram shape, which is the complete graph on 5 vertices. Every vertex is connected to every other vertex by exactly 1 edge. Notice that the 1 skeleton is a graph, and there's a foolproof way to find the fundamental group of a graph. First, we find a spanning tree, and a spanning tree is contractible, so we can collapse it. Everything in red will be identified together into a single point. What we end up with is a wedge of circles. For the technical details, the graph and the spanning tree form a good pair, and so the quotient map obtained by collapsing the spanning tree is a homotopy equivalence. Therefore, these spaces have the same fundamental group. It's just the free group generated by each of the edges that is not in the spanning tree. Indeed, if we have a loop that is entirely inside the spanning tree, then since the spanning tree deformation retracts to the base point, the loop is null homotopic. The only way we can get something that is not null homotopic is by winding it around a hole. And this only happens when we cross over an edge that is not inside the spanning tree. In this case, we can't contract the loop to the base point anymore. As a loop winds its way around the 1 skeleton, we can write down every time it crosses one of the edges that is not inside the spanning tree. And the resulting word we obtain sort of encodes that loop. Loops are homotopic in the 1 skeleton if and only if they cross the same edges in the same direction in the same order. That is, they have the same reduced word in the free group. Having figured out the top of the quotient, we now handle the bottom. Consider C1. The attaching map of C1 is given by the path that winds its way around the boundary of C1. In this case, the reduced word corresponding to this path is just E. But notice that this loop was previously stuck around a hole that's no longer there, because C1 now fills that gap. So we can now contract this loop to the base point by sliding over C1, and we find that E is equal to the identity. The same thing happens for all of the other 2 cells, C2 through to C6. The reduced word of the attaching maps is now more complicated, but we can again contract each of the loops to the base point by sliding over the corresponding disk. We obtain a list of relations, one for each disk. Each comes from a loop that was not null homotopic in the 1 skeleton, but has now become null homotopic after gluing in the 2 cells. Taking a quotient by the normal subgroup is really the same thing as the following group presentation. Suppose we have some loop inside of P. Notice that we can always push it into the 2 skeleton. And in fact, we can do better. We can push it into the 1 skeleton. But a loop inside the 1 skeleton, that's always given by a reduced word. We just note down whenever we cross an edge that's not inside the spanning tree. So it follows that we can generate the fundamental group using these generators. Suppose we have a homotopy between 2 loops, gamma and mu. This is a map from a cylinder into P. In this diagram, we identify the top and bottom edges to form the cylinder. The left edge corresponds to the loop gamma, and the right edge to the loop mu. As we slide across the cylinder, we see that the homotopy deforms the loop gamma into the loop mu. In fact, this homotopy traces out a surface inside P. Just as a one-dimensional loop could be pushed into the one skeleton, so too can a two-dimensional surface be pushed into the two skeleton. So we see that we can assume, without loss of generality, that homotopies in P are really homotopies in the two skeleton of P. Taking a closer look at a homotopy in the two skeleton, as we begin sliding gamma towards mu, we see that the loop slides across a disk, in this case C4. As this happens, we apply the corresponding relation coming from C4 to the reduced word. As we continue sliding toward mu, we slide across another disk, this time C6. Again, we apply the relation from C6 to the reduced word. In fact, sliding across two disks is all that a homotopy can do. We won't go into the finer details of the proof in this video, it's better to read an actual proof of the theorem, but all this is to say that loops are homotopic in P if and only if the reduced words can be obtained from each other by using only the relations coming from the attaching maps. So it follows that this group presentation really does give us a description of the fundamental group of P. Earlier in this video, we thought about what it would look like to fly through the Poincaré sphere on a spaceship. We thought about homotopies of loops. We thought about identifying opposing faces of a dodecahedron. We were thinking about geometry. If we reflect on the purpose of the Seifert-van Kampen theorem, we find that its power is in its ability to systematically distill all of the geometry and all of the topology of P into a simple list of 6 relations. And for the rest of the video, these 6 relations are all we'll need. Together, we've just crossed this bridge into the land of algebra and group theory. We proceed by simplifying the group presentation. We can get rid of the generator E, it's equal to the identity. And then we can substitute the first relation into the other relations. Now notice that after this substitution, none of these relations contain x, and x itself can be written in terms of the other generators. We can eliminate x without changing the group. And we can repeat this, subbing in relations and eliminating redundant generators. Each time we perform a substitution, do you see in your mind's eye the loop sliding its way over the 2 disk? Now that we're down to 2 generators, it turns out we can't reduce any further. However, the relations are still a little ugly, and we can clean them up by using a change of variables. We introduce a new generator S. Since it's entirely in terms of T and V, the group doesn't change. By rearranging and then substituting S, we obtain a much nicer relation. And the same is true of the other relation. Finally, we can write V in terms of S and T, and so it can be eliminated. After some final rearrangements, we obtain the following presentation for the fundamental group of P. Returning to our steps, now that we have an explicit group presentation, it becomes really easy to show that the abelianization is trivial. In our case, the abelianization just consists of adding the commutator relation st equal to ts to our group presentation. From here, it takes just a few lines of algebra to show that T must be the identity, and shortly thereafter that S is also the identity. So both generators become trivial, and therefore the abelianization is trivial. And with that, we've shown that P is a homology 3-sphere. It remains to show that the fundamental group is non-trivial. There's more than one way to do this, but for this video I've selected an approach that I hope you'll agree turns out to be quite pleasing. Consider the following argument. Let G be some non-trivial group, and suppose we find a surjective group homomorphism from the fundamental group into G. Then surjectivity implies that the cardinality of the source is greater than the cardinality of the target. Therefore, the fundamental group of P would have more than one element, forcing it to be non-trivial. So what could we take G to be? Well, in fact, G hides in plain sight. Consider the dodecahedral group. This is the group of rotations of a dodecahedron that keep it looking the same. Each of these rotations is given by a choice of which face is left pointing up and a choice of how that face is rotated. So in total, there are 60 ways to orient the dodecahedron. What are the generators of this group? Well, consider rotating around a vertex by 1/3 of a full revolution. We'll call this element S. We could also rotate about a face by 1/5 of a full revolution. We'll call this element T. These two elements, S and T, are enough to generate the entire dodecahedral group. Any of the 60 orientations of the dodecahedron can be reached by applying some sequence of rotations, S and T. So now we have some generators of G, but what about the relations? Well, we already saw some of those. If we do S 3 times, that's the same thing as doing T 5 times. But also, if we do S, and then T, and then S, and then T again, that's also the same thing. So the relation S cubed equal to T to the 5th equal to ST appears. Indeed, there might also be some other relations. For instance, we also saw the following relation, and in fact it is possible to show that these are the only relations in G. Consider the map from the fundamental group of P into G that sends S to S and T to T. Since every relation in the source is also a relation in the target, then this map is a well-defined group homomorphism. And since we map to all the generators in the target, this map is surjective. So by the earlier arguments, the cardinality of the fundamental group of P is greater than 60. Hence we've shown that the fundamental group of P is non-trivial, and we can conclude that P is not homotopy equivalent to the 3-sphere. As a side note, G has a number of other names. For instance, it's also the alternating group A5. It also happens to be the icosahedral group, which is the group of rotations of an icosahedron that keep it looking the same. In fact, it can be shown that the fundamental group of P has 120 elements, double the number of elements that G has, and it is commonly known as the binary icosahedral group. If we consider the generators S and T, we can see that there is a 1-to-1 correspondence between rotations of the dodecahedron and rotations of the icosahedron. Rotation about the vertex becomes rotation about the face, and vice versa. The dodecahedron and icosahedron are known as dual polyhedra. We can turn a dodecahedron into an icosahedron by turning faces into vertices, vertices into faces, and rotating the edges around. But what we are really describing is a process of changing k cells into n-k cells, where here n equals 2. Within these dual polyhedra is the essence of Poincaré duality. Returning to Poincaré's conjecture from the beginning of this video, we see that it is not true. We've described a space P and shown that it is a counterexample. But Poincaré revised his conjecture. What if, he wondered, a 3-manifold was both a homology 3-sphere and also had trivial fundamental group? This would rule out P, but would it be enough to guarantee that the space was homeomorphic to the 3-sphere? This statement turns out to be incredibly difficult to prove. Early efforts by Whitehead in the 1930s allowed him to show that a homology n-sphere with trivial fundamental group must be homotopy equivalent to the n-sphere, but this doesn't imply homeomorphism. The generalized Poincaré conjecture asks if a closed n-manifold, which is homotopy equivalent to the n-sphere, is homeomorphic to the n-sphere. When I first read about this, it seemed to me that the generalized conjecture should be a lot harder. If we can't even solve the n equals 3 case, why try larger dimensions? But it turns out that having more dimensions to work with is actually really useful. And in 1961, Smale comes along and proves the H-cobordism theorem, which handles the generalized Poincaré conjecture in all dimensions greater than or equal to 5. Then, in 1982, Friedman figures out topological 4-manifolds, and this gives him all he needs to show the generalized Poincaré conjecture for for n equal to 4. So the original question about 3 manifolds was all that remained. Still in 1982, Hamilton invents the theory of Ricci flow, in part to attack the n equals 3 case of the Poincaré conjecture. But he can't quite figure out how to do it. It wasn't until 2002 that the, at least topological, Poincaré conjecture was finally settled. Perelman solved the 3-manifold case, as well as Thurston's geometrization conjecture, by advancing the theory of Ricci flow. For 100 years, Poincaré's ideas about topology, his duality theorems, and his conjectures have motivated mathematical research and led to the creation of new fields of study which continue to interest us up to the current day. All of that inside of a D12.